This text describes the necessary libraries and modules for working with financial data and building a neural network model for time series data. Here is an overview of each component and its purpose. 1. Matplotlib. pyplot**, used for creating data visualization such as charts and plots, essential for displaying data and model results. 2. NumPy, NP, ***, a library for efficient numerical computing in Python, supporting large multi-dimensional arrays and matrices. Useful for handling financial data as arrays efficiently. 3. Pandas, PD, ***, a powerful data manipulation library that simplifies working with structured data through structures like data frames. Commonly used for data analysis tasks. 4. TensorFlow, TF, ***, an open-source machine learning library by Google, providing tools for building and training machine learning models. Used in this code to construct a neural network model for time series data. 5. Y-Finance ***, enables downloading financial data, e.g., stock prices, from Yahoo Finance, facilitating data acquisition for analysis and model training. 6. Train_test_split**, function from scikit-learn's model_selection module for dividing the dataset into training and testing sets, crucial for evaluating model performance. 7. Sequential, layers, optimizers, metrics, timeseries generator ***, classes and functions from TensorFlow designed for creating neural network models. Sequential for building layered networks, layers for adding network layers, optimizers for training optimization, metrics for performance evaluation, and timeseries generator for preparing time series data for training the neural network. In conclusion, the code sets up the necessary tools for managing financial data, data splitting, and constructing a neural network model with TensorFlow for time series data analysis and forecasting. This text describes using the Y-Finance library to download historical stock price data for Microsoft, MSFT, from the Yahoo Finance API. The data is retrieved for the past 730 days in 1-hour intervals. The downloaded data is then displayed using df. Head, showing details such as timestamp, open, high, low, close, adjusted close, and volume for each hourly interval within the specified period. This code is used to fetch historical stock price data for analysis, modeling, or visualization in Python, enabling efficient access and manipulation of financial data. To create a line plot of the open column in a dataframe named df, the following steps are taken. 1. The code retrieves the open column from the dataframe df. 2. It then uses the plot function on this column to display a line plot of the data within the column. Line plots are effective for observing trends and variations in data across time. They provide insights into how the values in the open column are evolving and facilitate an understanding of data behavior. By visualizing data through this method, it becomes possible to uncover patterns, connections, and irregularities that may not be immediately obvious from the data itself. This visualization aids in data-driven decision-making and the formulation of insights through plot analysis. This is a tool for generating a plot illustrating the values in the volume column of a dataframe named df. The plot displays how the volume data fluctuates across the index of the dataframe. Employing the plot function aids in visualizing data, exposing trends or patterns that might not be readily apparent from numerical analysis alone. It offers a detailed visual depiction that can support data-driven decision-making. This snippet isolates the open column from a dataframe and reassigns it to the variable df. It is a way to filter the dataframe so that only the open column is retained, while discarding all other columns. This can be beneficial when you need to concentrate on analyzing or processing a particular column of data without the interference of other columns. It can streamline data manipulation and enhance code efficiency by minimizing unnecessary data processing. The dataset is being divided into 3 parts: training set, validation set, and test set. Here is the process. 1. Extract values from dataframe df and store them in X variable. 2. Use train_test_split function to split arrays or matrices into random train and test subsets. This function is available in machine learning libraries like scikit-learn. 3. Split the dataset X into X_train_val, training plus validation, and X_test, testing, with a 90:10 split ratio, and data shuffling is disabled. 4. Further divide the training plus validation set X_train_val into X_train, training set, and X_val, validation set, with an 80:20 split ratio, without shuffling the data. Dividing the dataset into training, validation, and testing sets is crucial for proper training and evaluation of machine learning models. The training set is utilized for model training. The validation set is for hyperparameter tuning and assessing model performance during training, while the test set is kept separate for final evaluation to gauge the model's performance on new, unseen data. Data splitting helps in avoiding overfitting and provides a more trustworthy estimate of the model's performance. This process uses TensorFlow to normalize input data. Here's the breakdown of the steps. 1. A normalization layer, TF. Keras. Layers. Normalization, as created with the axis equals -1 parameter to normalize data along the last axis, typically the feature axis. 2. The normalization layer is then adapted to the training data, X_train, using the adapt method to calculate the mean and variance for normalization. 3. The training, validation, and test sets, X_train, X_val, X_test, are normalized with the trained normalization layer. 4. An inverse normalization layer is created with the same axis and invert equals true, to revert the normalization during inference and restore the original datascale. Normalization is a standard preprocessing method in machine learning to homogenize input feature scales. This aids in enhancing training performance and convergence for various models. Normalizing input data ensures that the model learns effectively without being influenced by varying feature scales. This sequence of steps likely involves rescaling the normalized X_train data back to its original scale using an inverse normalization technique and then plotting both the rescaled data and the original data on the same plot for comparison. Normalization is a standard preprocessing step in machine learning to scale data within a specific range. After training the model and predicting results, it is typical to inverse normalize the data for better comprehension and interpretation of the outcomes. Comparing the original and rescaled data through a plot can offer insights into the model's performance and how the data was transformed during the process. This process is crucial as it aids in visualizing the effects of the normalization technique on the data and assessing the model's performance. Contrasting the normalized and original data can also help in identifying any scaling issues that could have influenced the model's performance. The timeseries generator class is being used to create batches of temporal data for a machine learning model. Here is an explanation of each component. 1. Window size. This variable determines the size of the window used to create samples from the timeseries data. In this case, the window size is set to 60 time steps. 2. Batch size. This variable specifies the number of samples in each batch during training or validation. Here, the batch size is set to 32. 3. Train data generator. Instance of the timeseries generator class created for training data. It takes the normalized training data, norm_x_train, as input to generate batches of samples with the defined window size and batch size. 4. Validation data generator. Instance of the timeseries generator class created for validation data. It takes the normalized validation data, norm_x_val, as input to generate batches of samples with the same window size and batch size. The timeseries generator class is commonly used in tasks involving sequential data, like time series forecasting or sequence prediction. It helps in creating input-output pairs from sequential data for training and evaluation. Using data generators allows efficient handling of large datasets, varying sequence lengths, and prevents memory issues in machine learning models processing sequential data. This neural network model is created using Keras. Here is a breakdown of what the code does. 1. Sequential model creation. Creating a sequential model initializes a linear stack of layers. 2. Adding an LSTM layer. An LSTM, long short-term memory, layer is added to the model with 64 units. The input shape specifies 60 time steps with one feature for each step. 3. Adding a dense layer with ReLU activation. A dense layer with 8 units and ReLU, rectified linear unit, activation function is added. 4. Adding a dense output layer. An output dense layer with 1 unit is added. 5. Printing model summary. The summary of the model, including details of each layer, output shape at each step, and total number of parameters, is printed. This code defines the architecture of a neural network model for tasks like time series prediction and sequence modeling. The LSTM layer is effective for handling sequential data by retaining information over time steps. Dense layers with activation functions aid in learning intricate patterns in the data. The model summary provides an understanding of the model's structure for debugging, optimizing, and evaluating complexity. This text describes the architecture of a deep learning model built using the Keras library with a TensorFlow backend. The model is a sequential model composed of multiple layers. 1. The first layer is an LSTM layer with 64 units, designed for processing sequential data. It expects input sequences of a specific length and one feature per time step. This layer is set to return sequences as output. 2. The second layer is another LSTM layer with 64 units, also configured to return sequences as output. 3. The third layer is an LSTM layer with 64 units, but this one does not return sequences, providing a single output for the entire input sequence. 4. A dropout layer with a dropout rate of 0.2 is included to prevent overfitting by randomly deactivating some input units during training. 5. A dense layer with 8 units and ReLU activation function follows. This layer applies a linear transformation and ReLU activation to the input data. 6. The final layer is a dense layer with 1 unit, acting as the model's output layer to produce a single output value. It uses linear activation by default. This model architecture is specifically designed for tasks involving sequential data. By stacking LSTM layers with dropout regularization and dense layers, the model can capture intricate patterns in the input data and make predictions accordingly. The ReLU activation function introduces non-linearity, while the final linear output layer is suitable for regression tasks requiring the prediction of continuous values. This text describes the training process of two models, Model 1 and Model 2, using a training dataset generator, train_data_generator, and validating them using a validation dataset generator, val_data_generator. For each model, 1. The model is compiled with the Atom optimizer and mean squared error, MSE, loss function. Additionally, metrics such as mean absolute error, mean squared error, mean squared logarithmic error, and root mean squared error are added to track the model's performance during training. 2. The model is trained using model.fit, where the number of training epochs, num_epochs, is specified, and validation data is provided to assess the model's performance on unseen data. Employing the specified optimizer, loss function, and metrics helps in optimizing the model's parameters during training and evaluating its performance. Training the models for a specific number of epochs enables them to learn from the training data and enhance their performance gradually. The validation data plays a crucial role in evaluating the model's generalization capabilities on unseen data. This text describes the visualization of training and validation loss curves for two different models. Each model's curves are displayed on a single graph, with the x-axis representing the number of training epochs and the y-axis representing the mean squared error, MSE, loss value. Lower MSE values indicate better model performance. The training loss curve shows how the model improves on the training dataset over epochs, while the validation loss curve indicates the model's performance on a separate validation dataset. The curves are plotted in different colors with labels to distinguish between the models. This visualization is crucial for comparing the performance of models, identifying issues like overfitting, when training loss decreases while validation loss increases, or underfitting, when both losses are high, and making informed decisions for model selection and fine-tuning to optimize performance. This snippet is a part of a machine learning model evaluation process. It involves two models, Model 1 and Model 2, that predict outputs based on val_data_generator input. The predicted values from the models are then passed through an inverse_normalizer function to reverse the normalization applied to the training data. This function restores the predicted values to their original scale or distribution, aiding in interpretation and analysis. The goal is to have the predicted values in their original form for better understanding and further analysis. The last line, actual_vals equals inverse_normalizer, norm_x_val, window_size, extracts the ground truth values from validation data not used for predictions and applies the same inverse normalization process as for the model predictions. In essence, this code is essential in ensuring that predicted values are converted back to their original scale post-evaluation for improved interpretability and analysis in machine learning models. This process computes various evaluation metrics to gauge the effectiveness of two models on a validation dataset. Key metrics include 1. Mean absolute error, MAE, measures the average absolute variance between predicted and actual values. A lower MAE signifies superior performance. 2. Mean squared error, MSE, computes the average of the squared errors between predicted and actual values. 3. Root mean squared error, RMSE, derived from the square root of MSE, it provides a similar view as MAE but is more responsive to larger errors. 4. Residuals determines the variances between actual and predicted values, which aids in understanding the error distribution of the model. By evaluating these metrics for each model, it becomes possible to compare their performance on the validation dataset. These metrics play a crucial role in appraising a model's effectiveness, identifying areas for enhancement, and facilitating data-driven decisions for optimizing or advancing the model. This visualization is created to compare actual values, model predictions, and residuals of two models on a validation dataset using multiple subplots. Here's an overview of the steps involved. 1. A figure is generated with dimensions of 12 by 6 inches to contain the subplots. 2. A subplot grid is established with 2 rows and 1 column. 3. The first subplot displays actual values plotted against time. Predictions from two models with their mean absolute error, MAE, and root mean squared error, RMSE, as labels. Title and axis labels are set, and a legend is added to differentiate between actual values and predictions from the models. 4. The second subplot displays residuals, differences between actual and predicted values, for both models against time. A horizontal line at y equals 0 to indicate 0 residuals for well-fitted models. Title, axis labels, and a legend to distinguish residuals from each model. 5. Subplot layout is adjusted for readability. 6. The figure is displayed to compare actual values, predictions, and residuals of the two models. This visualization aids in evaluating model performance by comparing predicted and actual values as well as analyzing residuals. It assists in identifying the strengths and weaknesses of each model in predicting variables like stock opening prices, enabling informed decisions on model selection and improvement strategies. This process evaluates the performance of two models, Model 1 and Model 2, by predicting on a test dataset. Here's a summary of the steps involved. 1. Initialization of a timeseries generator object uses norm_x_test data for both input and target, with specified window_size and batch_size. This generator creates batches of temporal data for the models. 2. Both Model 1 and Model 2 predict on the test dataset using the predict method with the test data generator. 3. Predicted values are then reverted to their original scale using an inverse_normalizer function to compare predictions correctly. 4. Test values, ground truth, are also converted back to the original scale from the window_size index, aligning with prediction start. 5. Metrics like mean absolute error, MEA, mean squared error, MSE, root mean squared error, RMSE, and residuals are calculated for both models using predicted and actual test values to evaluate their performance. This process is essential for evaluating how well two models perform on a test dataset. Generators aid in managing time series data efficiently, and normalization is crucial for comparing predictions accurately. The computed metrics offer insights into the predictive capabilities of each model when faced with unseen data. This visualization tool compares the performance of two models in predicting the opening prices of a dataset. The tool displays a figure with two subplots. 1. The first subplot showcases the actual opening prices alongside the predicted prices from each of the two models. Each model's predictions are represented by a line, with the mean absolute error, MEA, and root mean squared error, RMSE, also included for each model's predictions on the test data. 2. The second subplot illustrates the residuals, which are the variances between the actual values and the predicted values of the two models. A dashed gray line positioned at y=0 aids in visualizing the extent to which the residuals deviate from perfect predictions. This tool is essential for evaluating the performance of machine learning models on time series data, such as stock prices. It enables a comparison of model predictions with actual values and provides a visual representation of errors, residuals, to identify areas where the models excel or underperform. By offering insights into model selection, tuning, and enhancement, this visualization assists in making informed decisions. This text describes the process of evaluating performance metrics for a simple naive model used in forecasting time series data. 1. Initially, the code predicts values using a basic naive approach on validation and test datasets. The prediction for each point is based on the value of the previous point. 2. Following this, the code reverses the normalization applied to these predictions to return them to their original scale. 3. The code then computes metrics such as mean absolute error, MEA, mean squared error, MSE, root mean squared error, RMSE, and residuals for both validation and test sets. These metrics offer insights into the accuracy and error magnitudes of the model. 4. By examining these metrics, the predictive ability of the naive model can be evaluated. Lower values for ME, MSE, and RMSE indicate better performance, while analyzing residuals gives information on error distribution. In conclusion, this code snippet assists in evaluating the predictive quality of a simple naive model on time series data, enabling comparisons with more advanced models and enhancing understanding of the model's predictive capabilities. This text describes a visualization created using the matplotlib library, with 2 subplots. The first subplot compares actual values with predictions from the naive benchmark model, displaying mean absolute error, ME, and root mean squared error, RMSE, in the legend for reference. The second subplot shows the residuals, errors, of the naive benchmark model's predictions, with a horizontal line at y equals 0 for reference. This visualization helps evaluate the model's performance in predicting opening prices by visually comparing predictions and actual values, as well as analyzing prediction errors for patterns or trends. This analysis compares the performance metrics such as mean absolute error, ME, mean squared error, MSE, and root mean squared error, RMSE, of various models using validation and test data. It begins by showcasing the metrics for a naive benchmark model on both validation and test datasets. Subsequently, it evaluates the performance of 2 other models, Model 1 and Model 2, in comparison to the benchmark on the validation and test sets, providing the ME and RMSE values for each model. This evaluation is essential for assessing and contrasting the predictive capabilities of different models on new data. Through these statistics, we can determine which model offers greater accuracy in predicting the target variable. This type of analysis is critical for identifying the most effective model for deployment in real-world scenarios.